All right. So we're
Get
live.
us
I gotta
live.
get you probably some share permissions.
Yeah, I already clicked. I already tried.
All right. You have
Didn't
permission.
work.
You have permission.
Thank you. Here we are.
Nice. All right.
All right.
Cool.
Wait, is there anything? Cool. Hello. All right.
Hey, learners.
So I am. Hey, learners. Learners. Do you wanna?
Yeah.
So some more about your dogs?
Oh,
or?
sure. Yeah. So I got a new dog on Friday, and I was just telling Martin that they just kind of got a feel of each other. My other dog, I think now is like, yeah, okay, this new guy's living here with us. They're playing well together, but they're also like not as crazy as they were just from pure excitement from like the first 2 days that we got them, because they were just like on top of each other. We laid out all these mats in the apartment so that the downstairs neighbor, if they come up complaining about the noise, we can be like, look, we have all of these gym mats all over the place. We tried everything. Yeah, we're open to suggestions. Please let us know. So anyway,
so do they actually jump around on the gym mats, or
they do?
Do they like use them as fun stuff?
Yeah. So Regs is like, he knows on the mats. He knows to like, that's his play area, and now we added 3 more mats to the floor. So he knows when I say, guys, on the mats, like, or just I tell Regs to go on the mats, the other one, Jax, he follows. Hold on 1 second. What's happening?
What's happening? What's happening?
Hold on.
Something's happening.
No, Anyway, whatever. Doesn't matter. My computer decided to like... Where are we? Oops. Alright. Whatever. Anyway, my computer is like... One of the monitors just decided to not accept the signal anymore. So...
How many monitors do you have live?
2. My laptop and 2 more.
Gotcha. Okay.
Anyway,
I mean,
right.
I started this up. I think we're ready to, if we wanna, we're ready to keep going.
Yeah, let's do it. So last week we we learned all this like multi-label classification, and we said we were going to stop because we saw like in the beginning it was very clear this other computer vision problems, and within that we have multi-label classification and then regression. So
correct.
In this stream we're going to, after running all of this, we will just do the regression, and then on Thursday, the next stream, we're going to build something with multi-label. Ooh, do you want to stay on the pet breeds and take a photo of the 2 of these guys and see if they can get both pet breeds?
Sure.
For multi-label classification.
Yeah, we can do that.
But we have to train.
Yeah, I guess
we have to train on. Do we? Oh no. I wonder if we actually have to train on the different. Because here we have like what's on this screen, right? We got like the horse. This was horse person, right? Conclusion is a horse person.
Yeah.
So I wonder if we have to train on. If we do have to train for the dog breed classification, I mean, I guess we do, like 2 different dogs, and find a data set that has 2 different dogs.
That they're both in the same image, you mean?
Yeah. Unless
I'm not sure what this is able to classify. We could look at the labels. Mm-hmm. It definitely doesn't have all of those dog breeds in there.
Yeah.
I think we look at the labels at some point further down. I'm just gonna have to run all of this so we can continue where we left off. I mean, I guess we probably don't have to run this temp data frame.
Right.
Click, click. But this we need. Data block, data set. I mean, maybe actually we start with something new. I'm not sure about that. There we played around a bit, learned some stuff about the default split of training and validation. And then we choose a specific one, I believe, down here. After we define our, like how to split the data, get the labels, get the X's. Then, not yet, I guess that was also unnecessary. Indexes, there they are. Oh no, all right, this is how you can pick up the index from one. There they are. So yeah, I'm pretty sure there's no, look at that, that's all. We have dog, so it probably would just say dog if you feeded a picture of the two of them.
Yeah. But,
or dog person if you're in it too.
Right.
Here's our splitter. Now it splits it in a way that it was described in the data, in the CSV.
In the one hot encoded data, CSV.
Nice. Constructing, show the batch. Come on, come on, come on. Then this we also did, binary cross entropy. Make our learner, and then we have a bit of time for training. What's that? Train one patch. Oh, what's that? We saw that the model is general object of class. Grabbing a mini batch. This activations. Now it's going to come to this note. Martin, you don't understand activations. Oh no, loss. I don't know, one of those. Both. Loss
there
functions.
it is. There it is.
Are the ones that don't understand. Scroll. It's gonna make more sense if we just keep working on it. Yeah, okay, I remember that. This is the partial interesting stuff. Whoop.
Just out of curiosity, did you look up loss functions over the weekend?
I did not.
Okay, because I think there's a note. Was there a note somewhere for me too to figure something out, or no? Or maybe that was a previous thread.
Well, mine just says that I don't understand them. It's not an actionable task at all. So I believe there's something for you too, yes.
I thought there was.
Guten Tag, Nick. Let me see, we're training here.
There it
is.
is.
Look.
Yeah.
I need to go review the lesson we did with Gilad.
And I have
so,
not.
Yeah.
But I guess mine is more actionable. Yours is just a statement. I don't understand this. Mine is like, oh, I'm gonna go learn. So
yeah, see, if you don't put any actionable statements, you can't fail by not doing them.
Right, you're just stating.
Just stating a fact. Okay, so this is training. So I wonder, probably we're actually not gonna need this, huh? Did I do this in vain? I might have. Some plotting, and then we're at regression. Assemble the data. Let's just see whether I did it for nothing. Yes, I did it for nothing. Okay, so let's consider this a review. An unnecessary review without much. I thought it was you for a second. I saw the short hair. I was like, how did you get a picture of Nick? Okay, so yeah. Last time we did. No, we don't. Oh, please, we get some crap in our chat, Nick.
Yeah, I know. We gotta figure out how to do this in OBS.
Fun bots posting stuff. It's interesting how it's using all those different characters, right? Mm-hmm. To make it like not be recognized by.
Yeah, I guess so.
Automatic detection.
Mm-hmm.
I wonder why this is still working, honestly. Like, why wouldn't you just say that it's optional what type of P or what type of A? I guess there's so many different characters that you can make.
Yeah. Oops, I'm signing into to Twitch because I don't know. Is that something that you can like remove or? Oops.
I'm not sure. I think you probably would be able to mark it as spam or something, and then maybe it gets removed.
Okay, all right. Whoops, close. Oh, come on. Chat settings. Yeah, I don't know. Don't know how to do it. Oh, whatever. We'll figure it out.
You can't like click on it and say remove or
No.
mark as spam or something like that.
Oh, wait, hold on. Yeah, I can.
Oh yeah, and then we looked at this different metrics, I remember. That was interesting. Remember when we looked into the graph to figure out what was the best threshold to use?
Mm-hmm.
Ah, nice, yeah. We got them deleted. Thumbs up.
All right. So I wasn't paying it. Is this is still the previous one?
Yeah, I was just waiting for you and revisiting the end of this, and then remembering that we did. You remember this learning curve?
Yeah.
And then picking out a specific slice of it to see what's the highest, like where can we get the highest accuracy?
Right.
Okay. But that was last time. It's all in the past.
It is all in the
Today
past.
it's time for regression.
Yep. All right. Let's start. Let's start regression.
Cool. I can start reading.
Sure.
Regression. It's easy to think of deep learning models as being classified into domains like computer vision, NLP, and so forth. And indeed, that's how FastAI classifies its applications, largely because that's how most people are used to thinking of things. But really, that's hiding a more interesting and deeper perspective. A model is defined by its independent and dependent variables along with its loss function. It means that there's really a far wider array of models than just a simple domain-based split. Perhaps we have an independent variable that's an image and a dependent that's text. For example, generating a caption from an image. Or perhaps we have an independent variable that's text and a dependent that's an image. For example, generating an image from a caption, which is actually possible for deep learning to do. Or perhaps we've got images, texts, and tabular data as independent variables, and we're trying to predict product purchases. The possibilities are really endless. To be able to move beyond fixed applications to crafting your own novel solutions to novel problems, it helps to really understand the data block API, and maybe also the mid-tier API, which we will see later in the book. As an example, let's consider the problem of image regression. This refers to learning from a dataset where the independent variable is an image and the dependent variable is one or more folds. Image regression from a dataset, let me see again, where the independent variable is an image and the dependent variable is one or more floats. Okay. Often we see people treat image regression as a whole separate application, but as you'll see here, we can treat it as just another CNN on top of the data block API. What am I trying to do with this image regression? Do you understand that?
I was like sort of listening, and then I'm listening to the dogs murdering each other and on the other side of this wall. So I put the mic on mute for a second. No, could you just scroll up and I'll like skim through it to get a sort of an idea?
Sure.
Okay.
Wait, I'll leave that to you, and I'm just gonna get myself some sweets. I'll be back in a second.
Yeah, for sure. Okay, but really that's hiding a much more interesting and deeper perspective. A model is defined by its independent and dependent variables along with its loss function. That means there's really a far wider array of models than just the simple domain-based split. Okay, perhaps we have a more independent variable that that's an image, and a dependent, that's text, generating a caption from an image. Or perhaps we have a dependent variable, we have an independent variable, that's text, and dependent, that's an image, generating an image from a caption, which is actually possible for deep learning to do. Okay. Or perhaps we've got images, text, and tabular data as independent variables, and we're trying to predict product purchases. The possibilities are really endless. To be able to move beyond fixed applications to crafting your own novel solutions to novel problems, it helps to really understand the data block API. So I have mid-tier API. All right, we'll use that later. As an example, let's consider the problem of image regression. This refers to learning from a data set where the independent variable is an image and the dependent variable is one or more floats. Often we see people treat image regression as a whole separate application, but as you'll see here, we can treat it as just another CNN on top of the data block API. We're going to jump straight into somewhat tricky variant of image regression because we know you're ready for it. I mean, thanks guys. I don't think we are. I don't really understand anything that I just read in this little 2-paragraph blurb. Do you get any of this?
Well, I think so. What I'm wondering about is this: what's image regression pointing to?
Do you understand this idea, the dependent and independent variables of each other? Like, okay. So hold on. My understanding of this is, if you took like natural language processing and computer vision, and I said, show me a photo of a turkey, and then it takes that, understands that I want a photo of a turkey using NLP, and then makes that request with computer vision to, or actually, hold on. If I say like, what is in this photo? Is that something that?
Yeah. So the two examples that it's bringing is, one is like, where were we? Independent, dependent, loss function. Generating caption from an image. So one, I guess, what you were asking.
So a caption from an image.
What you were asking isn't in there, but there's like what you were asking would be a classification. You ask for, like, you show an image and you get what's in there, right? Is that what you just said?
Well, that's what it seems like. That's what generating a caption from an image is. So if I feed this turkey, it'll say, okay, we've recognized
a turkey
that,
on there.
Right, we've recognized that this is a turkey.
Correct.
But then I don't understand, is it combining computer vision and NLP, where it's
not NLP. It's just image and text. It's just saying, you know what the image is, and it's predicting the text. So it's combining these two aspects of it, like text-based and image-based.
But the text is, in our previous example, what the labels were.
Yeah.
So how is it?
That's it. That's the dependent variable. Well, okay, for the training, yeah, but you're predicting, like, that's just for the training set. But for the application, then it's doing the independent variables. You're feeding it the picture, right? And then, the dependent variable. No, I'm confused too.
Sorry.
Let's just. So if you think of the second one, there the idea is that you give it an image, and then you give it a word, and then it creates an image.
You give it a word. So if I give it a word, turkey.
Yeah.
It'll draw the image.
Yeah.
Or it'll go find the image.
No, it will draw it. It will create an image, like draw. It will make a photorealistic or whatever, however you trained it, image of a turkey.
Got it. So it's kind of like almost the opposite of classifying.
Right, yeah. Yeah, it's just like, depending on what are you feeding it, and like what do you want to create, essentially. In the first example, you give it an image, you want to create some text. In the second example, you give it some text, you want to create an image.
Right. And this creation of an image is it essentially just responding back with, well, this is kind of what this application thinks a turkey is, right?
Yeah.
This is what we're kind of classifying against. So if it
Mhm.
sort of looks like this, then we think it's a turkey. Is that sort of it? Or is there something that we have to like kind of add on top of it to draw this image? Yeah, I don't know. I'm just kind of like not really understanding. Like I'm actually okay moving past this because I think the way that maybe we assemble the data and the application will answer these questions. I'm okay like not knowing what it is at this point. And then if at the end of the stream I'm still like I have no idea, we could put a little note in there, but not one that makes me action.
I
it
don't
just tells
understand.
yes, exactly. I just don't understand.
I can also leave a note for me about what's the image regression idea, because the independent variable here is an image and the dependent one is one or more floats. I'm wondering what kind of like numbers they want to get out of the image.
Yeah.
Or maybe it's like lighting. Okay. All right. I don't need to make this note. I guess it's some sort of numerical value that describes something that's in the image. Like maybe gradients or could even be what?
Yeah, maybe. I have no idea.
Okay. We're going to jump right into some tricky variant. You already read that, huh? A key point refers to a specific location. We're going to do a key point model. A key point, specific location in an image. In this case, we use images of people, and we'll be looking for the center of the person's face in each image. This means we're actually predicting two values for each image, the row and column of the face center.
Cool.
Okay. Biwi Head Pose dataset for this section. Download the dataset as usual, because untar data obviously works with all of your datasets.
Right.
Datasets. Geo Zurich street site.
Is this what we're using? Oh, no.
Video segmentation. No, that's just a bunch of datasets. It's probably somewhere in there. Biwi. This one.
Head pose. Interesting.
Was it that one? Head pose?
Mm-hmm.
Yeah.
I saw yesterday, I was on TikTok and I was watching, there's this like new filter, this like, I don't know if it's, the TikTokers, the people on TikTok are calling it like a Disney princess filter or Disney character filter, but it basically like cartoonifies your face.
Mm-hmm.
And my goodness, like the gesture tracking, like of like your face and the movements and everything, it's like on a totally different level. I've compared to Apple's like Memoji technology. This one was like the eyebrows were just on point, and the way that you moved your mouth and like tracking everything, it was really, it was on point. It was cool.
What's it called?
Disney I don't know. Princess? I couldn't find it. Oh yeah, you could just do TikTok. Disney princess filter. Oh yeah, click on that first one because I don't know how to get it, and then I'll get it.
You're not gonna hear it though. It's really crazy.
I don't know if it's that one. Maybe it's the next one in that, like on their bottom scroll thing.
What?
There's like the Frozen character. So I think is this, it's like we can't hear it. Is this the one is that actually it, or?
I don't know.
Because we can't hear anything.
I mean, I can.
Yeah.
I can do like this.
Oh, we hear it now.
Page Piston.
No, you don't have to do that.
Is on the inside, and if you want to unlock and start a story, so let's just X out of this.
This is creepy. This is making me uncomfortable.
This one's not the one that I saw yesterday. I don't know where my phone is, but can we search a different one?
Okay. Give me your words.
I don't know. Cartoon filter TikTok. TikTok, cartoon filter TikTok.
How to get the cartoon filter? Do you think that's the one?
2 days ago, maybe. Oh wait, hold on. Let's see. What's
Snapchat.
There's something that's loading.
The filter has been taking over, but to find it, you'll actually have to head to Snapchat. Oh, so it's a Snapchat filter, it seems.
Interesting. Okay. Can you go to a different? I just want to show the like the tracking of the faces. Cartoon filter.
It's mining some cryptocurrencies in the back.
100%. Oh yeah, that first one. That first image. Like that's the cartoon face. That's the video that I saw.
Like this is how it makes the faces look like.
Yeah.
Dog.
But the facial tracking was just... I think that video is the one who said it as well. Like, I don't know. Click on that first photo. Oh no.
Disney dog. Which one?
That one. And see if it goes to the actual TikTok.
Looks like this is the same article we've just...
Oh, interesting.
Anyway. You should be able to find it. Yeah.
Or yeah, through videos or something.
It's the same thing. My computer seems to be really doing hard work.
Mm-hmm. No, it's not this one.
It's not the one.
No.
Huh. Maybe.
No, it's not
No?
this. No.
11th of August. I guess that's an older version. Well, you can search for it.
Yep.
And if you find it, you can let me know. Did you look at this at all? Did you hear about that?
Was this the ethics researcher?
Mhm.
Yeah.
What's your thoughts on that?
I didn't read the article, but the gist of it was that she was hired to lead it, and then they just like fired her silently. No.
She kind of like she voiced some concerns in an article that they wanted to publish about some of the effects of the AI research that was being done, or like things that we're doing. And she said she had some demands of like that things should change, or she would resign, and then they kicked her out. There's some interesting things in here. You can read it. Like I didn't know that. For example, like this is like what's the carbon footprint of training one of those big language models that this article is about. Like that's a lifetime of a car, and this is training this model. Or like compared to flights, right?
I didn't even see this.
So that's interesting. And then it also shows like, this is my takeaway from what I've read about it. Like it shows some different types of models and what the cost for training for those is. And this that's the big one that Google is currently running, or that they're using for their search.
Wow.
And it just takes like between $1 million and $3 million to train. And that has a carbon footprint of, I don't know, pounds. Is that pounds per?
Yeah.
Pounds of CO2. Right. And
So
anyways, the interesting thing is just, like my takeaway is like, how much better is this really than this, for example, right?
Right.
And is it worth it? I mean, I'm sure it's worth it for marketing for Google, but is it worth it on a humanity type
Totally.
scale, both for what it what it costs for the environment as well as it would just costs monetarily? And I'm thinking again
Sure. I
about
mean, if
whom
Google
it benefits.
if Google wants to spend $3 million training it, whatever, that's fine. But
Yeah,
wow,
that's a big difference, right?
600 tons of CO2.
Is that tons? 1,000 pounds is a ton?
Yeah.
That's a lot
Yeah, that's a lot.
for training, right? I mean, right, once it's trained, as we've seen in our tiny examples, it doesn't take that much energy anymore, but still.
But so like the interesting thing though is take that number, right?
Yeah.
And then just copy it for a moment and then go to Google and type in like cost to offset no. Let's do like
600. All right, it's big, generous.
600,000 pounds. So 600 tons.
Maybe. Think that works.
Why don't you do carbon offset calculator? Oh, there you go.
We got
right
something
there.
here.
Choose a unit. If you have, energy data.
Therms.
So actually, do kilowatt hours of electricity.
Oh, there you go.
Okay.
That should work, right?
Metric tons, or go to pounds and then just copy that exact number in.
Okay.
Yeah. So that our math is totally correct. $200 metric tons. So I think it's maybe 2,000 pounds is a ton. Anyway, so that's the same as 61 and a half cars driven for 1 year, or 700,000 miles.
Yeah.
Or almost 32,000 gallons of gas. Look at all those oils. So to train Google, it's to train this. So this is the natural, like the search, right?
Yeah, I think that's what they're using for search. Some language models that they're using for search, like
Right.
NLP models trained. 371 acres of forest.
So that's how much. Yeah, if you had 400 acres of forest, that's how much carbon would be sequestered per year.
Mm-hmm.
So
they'd have to plant 400 acres of forest.
No. No.
For an offset, no.
No. That's.
I mean, offsets are weird anyways. But
that would have to be. That's like what's there now. So like 400 acres of what's there, fully grown forest would be able to absorb this. So if you wanted to grow something, that's the first one. You have to have 4,696 trees growing for 10 years if you were to grow from scratch.
Huh. Yeah.
But there's my point is it sounds like a lot, but when you scroll a bit, like is there no cost to offset? It just shows you.
I guess it's just equivalencies.
Yeah. Go to carbonfootprint.com.
You know that one?
I don't know if they're gonna have how much it's gonna cost to offset. Okay, so let's do the US because that's probably where below.
Whoa. What are you doing?
Oh, forget this. This is
What is it doing? Reloading after every state? That's a footprint. Yeah, I don't think that's what we're
forget
looking
this.
for.
Forget this.
This maybe. Carbon credits.
Just type like offset my carbon footprint. Okay, and then
Add. Also funny that we're using this right now.
right.
I guess I should maybe switch if I'm serious about anything. Calculate. This is all annoying.
Yeah.
Google.
Technology.
Technology. Oh, I can't. This is dumb. Okay, this is just a. Yeah. Anyways, my takeaway. I don't know much about this. I heard about it, and I heard that I think it's nice that there's people being critical about is the use of this really worth the cost of it, essentially, I guess. And
So-
it seems kind of lame that they're firing someone for saying that.
Yeah. I'm trying to think like where so 1 second. So if you wanted to here, this is what I was looking at.
Do you want to share?
How many here, let me just paste it in chat.
Okay.
So let's see. Pounds to metric tons.
Oh, you're on the same page still.
How many pounds? 6,000, 600, 25,000. Go to that third tab or the fourth one. Really quick.
626,155.
626,155.
It doesn't. 626,155. Yeah.
So 284. So put that there.
What's that?
That's how many metric tons.
Uh-huh.
So to offset all of Google search, all these pounds is only $3,000.
That sounds absurd.
Yeah. So to offset a 1 metric ton of carbon, is $11.
Huh. Weird.
So it's definitely like bad for the environment and everything. But it's kind of like this weird thing that, well, we can just offset it for $3,000.
For $3,000, yeah.
Yeah.
I mean, yeah.
But, you know, at the same time, the question is like how many you need to have these projects available to fund to begin offsetting to get these credits. So,
And also how good, I mean,
and it's also like, but like to think about this in a different way, right? That other page said you need almost 5,000 trees growing for 10 years to get that, right?
yeah.
If you're training models like this, you know, we could, and let's say Google plants 1 billion trees tomorrow just to offset their training data and all the other stuff that they're doing. Sure. I mean, it's just going to take 10 years to offset what you're doing today. You know?
And it's not that they are not going to train any other models.
Yeah.
In the meantime.
Yeah. Also, carbon, you know, gets released from the trees as they're like when they die and they start,
right,
you know, decaying. So anyway. Back to it.
Interesting though that this is such a low number. Because that would mean like if a car.
Oh yeah, personally to offset your whole thing, your whole like,
your
life for a year is like $30, $40, something like that. It's not a lot.
That's weird, huh? Yeah. It's interesting.
Yeah, a shipping container from Shenzhen to Los Angeles costs like 10 cents to offset the shipping cost.
Whoa.
So it's crazy. So these companies should be doing it. They're just not. Well, a lot of them aren't. But it would cost pennies to, you know, offset, donate to projects and NGOs to, you know, do all this stuff. But anyway. Back to the Biwi Head Pose.
Yeah, very sidetracky today, huh?
It seems like it, yeah.
Okay, where were we? We were at the very beginning, assembling the data.
Yep.
So data set. We got the path, and in this path we have a lot of objects. There are 24 directories numbered from 1 to 24, which correspond to the different people photographed, and the corresponding .object file. 02, there's the directory, and then there's the object file. Let's take a look inside one of these directories. Okay. I should get rid of those. I remember I did that last time. Clear output. So that we have more fun. Clear output. Okay. Inside the subdirectories, we have different frames. Each of them come with an image underscore RGB and a pose file underscore pose.txt. So here's a pose and then there's a image. We can easily get all the image files recursively with the get image files, then write a function that converts the image file name to its associated pose file. Okay, sure. Image files, get image files from that path, picks out all of the image files with, we know that already, with common image endings. So they're going to pick all of these JPEGs, and then we are defining a function in this beautiful way that keeps confusing me. Returning a path object that takes, that takes string x, whatever we pass in there, which is the name, it's the name of the image file. Let me just play with that a second. Image files 0, what we get if I run this. Okay, so a path object that is from the root is in folder 5, and then it's that image. Okay, and then we're just actually taking the name of this, so we're taking .name of it, I believe. Oh no, we're doing string just calling it to a string. What does that do? Okay, so this gives us the full path, nice absolute path to the image file. So we're taking that, cutting off the last 7 bits, 1, 2, 3, 4, 5, 6, 7, up to here.
And just tacking
And then
on
instead,
pose, yeah.
Yeah, cool. Let's take a look at our first image. So they are using this, look, this PIL. You remember last time we were like wondering how to show an image?
Yeah.
Seems that it's the way that they do it in here too. Hi. Okay, the Biwi dataset website used to explain the format of the post text file associated with each image, which shows the location of the center of the head. The details of this aren't important for our purposes, so we'll just show the function we use to extract the head center point. We are a little bit interested though, right?
In what?
Right. In the way that they describe the poses.
Oh, in the to view the text, the pose text file. Sure. Yeah.
Let me see. I can just do that. Well, maybe I need the whole path. Okay. So this describes somehow how the head is oriented in the image. I wonder which parts of it describes. I assume it's going to be the eyes, probably the nose and the mouth. And then maybe ears.
Yeah, so let's look at what is it actually calculating.
So calculate numpy generate from text, gen from text. Interesting. Path 01 rgb.cal skip footer 6. I don't know what you do. Gen from txt. Get the image to post, get the post, so this access to this file. Skip the header. I wonder what's the header here. Skip 3 lines, maybe 1, 2, 3. So maybe it's just looking at this line. This function returns the coordinates. It's a tensor of 2 items. We can pass this function to data block as getY, since it's responsible for labeling each item. GetY is responsible. We'll resize the images to half their input size just to speed up training a bit. One important point to note is that we should not just use a random splitter. The reason for this is that the same people appear in multiple images in the dataset, but we want to ensure that our model can generalize to people that it hasn't seen yet. Each folder in the dataset contains the images for one person. Therefore, we can create a splitter function that returns true for just one person, resulting in a validation set containing just that person's image. Interesting. So we're taking out for the validation set. I think that's what I'm understanding. For the validation set, we completely take out one person.
Okay.
And we're going to validate the performance of the algorithm on a person that it has never seen before. The only other difference from the previous data block examples is that the second block is a point block. This is necessary so that FastAI knows that the labels represent coordinates. That way it knows that when doing data augmentation, it should do the same augmentation to these coordinates as it does to the images. Interesting. Like if it does data augmentation by like stretching something or cutting it, these points are gonna also be adjusted in the same way, the coordinates, so that it's still at the same, like at the same point in relation to the image.
That's cool.
We make a data block, an image block, and a point block. Point block is going to be the coordinates, yeah. get image, we use get image files, get y, get, what was that? This one. Get the stuff from the, extract it from the variable into the coordinates from the text files, splitter, lambda o dot parent name equals 13. So everything where the folder name is 13, so the whole folder 13 is going to be the validation set. And then we apply a batch transform on all of them, augmentation transform. Where do we cut them in half? Wasn't there something where we apply it first, that they all are smaller? Or is that this? It looks like an augmentation transform.
Was that like a normalize? Oh yeah, normalize from stats image net stat. I thought it was.
I don't know what that is.
I thought we were. Anyway, it could just be something totally different, right? That we're doing here.
Yeah. Look, interesting. The thing we thought was cool seems to be, I think, just for fast AI.
Points in data augmentation. We're not aware of other libraries that automatically and correctly apply data augmentation to coordinates. That's pretty cool. It's cool that they did that.
Okay, you keep going.
Okay. So before doing any modeling, we should look at our data to confirm it seems okay. So DLS, Biwi data load is okay. We're going to show, do we get more than 9 images? Or is this it? Yay!
This one works. What's different? I don't think we ever passed in a number. We usually just passed a row and column.
I wonder if we did, if we looked at show batch, if the default is just 9 and we never pass like the max n.
But was it, maybe we're going to get to the bottom of this.
Well, look, if you go, hold on, go scroll up. So figure size 8x6.
Yeah.
Right. If you just change n 12, so max n 12, change that to whatever, change it to 36, right? 6x6.
It's just gonna,
but let's say if we get 36 images and it's still
I think
within,
we do, yeah.
I'm trying to think of like, yeah, and it still stays within that bound. So we have 6 going across and 6 going down.
And we can make this bigger.
And it won't change.
It will have the same amount of images, but it's gonna go further out. Like this is like a graph, like a drawing board, the figure size.
Right.
See, yeah. I guess 12.
12 is horizontal.
Right. So if I do 14, 8 or something, it's gonna spread more horizontally.
If you do like 5, 18. It's trying to fill. It's trying to fill the vertical one first, it seems.
Oh, that's why it's spreading it out, you mean?
Yeah. So if you did that one as like 3 and 9, you'll get 36, right? Oh no, 4.
We always get 36
9.
images. That's just the size of the. Right. So now it's 3
9.
wide and 9 high. It makes more sense to have it like 9. So 9 wide and 3 deep. Now it's gonna have the opposite shape, like long down. Right.
Huh.
But this is much
but why are we getting
more
36 images still?
Yeah, because it's always, that's the number we're giving it here.
Yeah, I know, but if we're saying we only want 9 by 3, that's 27.
No, this is not the number of images. The figure size is just the size of the output. Like the canvas it's drawing on.
Okay.
It doesn't have anything to do with the number of images.
Got it.
If I do 2 here, it's still gonna have the same shape. Just only displaying 2 images. One next to the other one, probably. Yeah. See? Like it's the same.
Okay.
But this is much more intuitive than the one that we tried before, to me, because I mean it was intuitive too, apart from the fact that it wasn't displaying more than 9. Max number. So that's the default.
Yeah. There we go. We figured it out.
There we go. But interesting that.
8
but
streams later.
Didn't we used to pass something like a row number, like row and columns?
That's what I thought. That's what I thought figure size was. But maybe I misunderstood.
It seems like there's a bunch of keyword arguments you can pass. And then maybe there's an option that you do it with rows and calls instead of figure size.
Well,
let me try that.
Well, today I learned what max n was, and then I also learned that quargs stands for keyword arguments. I did not know that. I thought it was like a made up word. It's just one of those things that I've never really questioned. I was like, oh, okay, that's what it's called.
Yeah, args is arguments and quarks is keyword arguments. Yeah, that doesn't quite do it, I guess.
Yeah, I thought it was like a science fiction reference that I didn't get from like some show that the creators of the language just really liked or something.
I mean, it's not unlikely.
Right.
I'm really curious now how we did that. What was that? I guess we could also look, but today is the day, right? Yeah. Today is the day of digressions.
Regression.
Nice. I think we saw it. Yeah, for sure. We saw it in here. Regression, digressions. Show batch. Come on, I know you're in there. You're just hidden somewhere. Aren't you? Hey, max n. Okay. What?
Oh, n rows.
Did we always do that? Did we always pass n max max n? No, but maybe it was just n rows. Sometimes. N rows, 3, and then if we don't pass anything else, and then probably this n calls also. Yes, look at that, and we get onto 3 is 9 default images. And then if we do n calls 4, we're still only gonna get 9 because our 1, 2, 3, 4, 8. There it is, because
we got 9, yeah.
Max n defaults to 9. So if we say 12, now we can finally fill it up. Bam. Whew.
Good job.
Good. That feels good. It feels good.
Good job.
Okay, I shall leave a note. That feels good. Success. The mystery
is solved.
The 9 default 9 show batch.
Oops.
Method has been resolved. Sweet. Oh, now it's thinking that this is a. No, I'm not that megalomaniac about it. Okay. Whew. That makes me happy. All right. Nick, you want to go on?
Sure. Is this what I wasn't looking at? Is this what you write? Oh, success. Success. The mystery of the default 9.show batch method has been resolved. That's looking good. As well as looking at the batch visually, it's a good idea to also look at the underlying tensors, especially as a student. It will help clarify your understanding of what your model is really seeing. Okay. So XB, YB, the LS1 batch, shape, Y shape. So we got 2.
So that's the number of images in a batch, right? 64. And then 3 to 40, 320. What is that?
Make sure that you understand why these are the shapes of our mini batches.
I don't yet. Maybe you can explain.
No.
No, it doesn't look like it.
Did we miss something?
I don't think so. I mean, I'm sure we missed a ton. Okay, so something in here needs to be.
So wait, hold on. 240 by 320. Is that the image dimensions? Scroll up. The augmentation dimensions.
Sorry, I got lost where?
So that 64, 240, and 320. The last two numbers. Is that the image dimensions?
Right. I think so. You're right. I think you're right. That's
right,
yeah. There it is.
240 by 320.
So that's the size. Okay.
So we have the batch size 64. The last two are the image dimensions. What is the 3?
I think could that be something about that? It's a 3. What was that called? Rank 3. No, that would be a rank 4 tensor, right? Because it has 4 entries.
Mm-hmm.
Okay, so this is something else.
We got 3 numbers that we got to figure out. The 3, and then the 1 and the 2 on the other side.
And this is going to be Y. So these 3 are related to the labels, which we know consist of 2 coordinates. So that's probably the 2 number, I assume. Right? Here. This is like one label.
And you're saying because there's 2 coordinates, you have to feed that number 2 so that they know.
I think that's what the 2 means. Yeah, that's my assumption. Like, right, because it's similar to the dimensions of the pixel rows, right?
Mm-hmm.
I don't know. That's my guess here, that this is the 2, and then the 1 and the 3. I don't know. Okay.
We're really we're not sticking to the whole no actionable tasks.
Oh no, they're actionable for you and not actionable for me. I thought that was the plan.
I see. Okay. All right. Okay.
I mean, that's the precedent we set, right? You gotta stick with some traditions. Right? We're good.
Are we good?
We're good.
Nick makes sure that Martin understands why these are the shapes of our mini batches. Here, okay.
All right, let's keep going.
Here's an example of one row from the dependent variable. So YB tensor point, okay.
One row from the, okay, so interesting. So YB dot shape, and then this is what we're getting. We get a tensor
YB
point.
0.
Yeah, I mean, that's just one example, is what they're saying.
Yeah, but if YB is up there and you're printing YB, wouldn't YB 0 be 64? Like, what is this tensor point?
No, this is one. We're looking at one of the 64 tensor points that are in there.
Okay, gotcha.
Like that should be the last one, right?
Oh, right. Right. Dot shape is for the whole.
For all of it, yeah.
Yeah. Gotcha. Okay.
So we're looking at one of them, which means these two numbers should still be applicable, probably.
To all of them.
Each single one of them, yeah, right. I think. Or something. I don't know. I don't really understand it, I guess.
Yeah. Okay.
But yeah, this is how one of them looks like, I guess. As you can see.
As you can see, we haven't had to use a separate image regression application. All we had to do is label the data and tell FastAI what kinds of data the independent and dependent variables represent. It's the same for creating our learner. We will use the same function as before with one new parameter, and we will be ready to train our model. All right, maybe in training the model, we'll understand.
As usual, we can use CNN learner to create our learner. Remember way back in those angular brackets, how we used Y range to tell FastAI the range of our targets? Do I remember? Do you remember?
To tell the range of our targets?
Well, we'll do the same here. Coordinates in FastAI and PyTorch are always rescaled between -1 and +1. Okay. The range of our targets. Okay, so we're going to rescale them. Why? Between -1 and +1? Y range is implemented in FastAI using Sigmoid range, which is defined as define Sigmoid range x low high return torch.sigmoid x times high minus low plus low. That's the sigmoid range.
So now it's going to translate the sigmoid. Before it was between 0 and 1. Now it's going to be between -1 and 1.
I think so. I'm not sure why, but yeah, it's a sigmoid function and it goes between -1 and +1.
Okay.
This is set as the final layer of the model if Y range is defined. Final layer of the model. Okay. Take a moment to think about what this function does and why it forces the model to output activations in a range low high. Okay. Not the brains for it right now.
Yeah, neither
torch.sigmoid.
Neither do I.
So it does the sigmoid on it already, and then the output of that gets multiplied by high minus low plus low. Sounds very mathematically.
I'm gonna go put a sweater on. And
right now?
Okay. Right now. It's chilly in here.
Bye.
Well, I'm also gonna take time to think about applying this. Yeah. I think you should also think about it.
Okay. So what can I Google here? I can close. That's fine. How to recalculate a sigmoid function TP. Oh, great. Sigmoid range -1 to 1. Normalizing to 0, 1 versus 0, 1 versus -1, 1. You're not training out of range. Negative. So sigmoid range -2, 1. Normalizing was of -1 to 1 before feeding them the ML model. The ML model is most likely a few convolutional 2D layers followed by fully connected layers. Assuming activation functions is ReLU. My question is, would normalizing images -1 1 range be unfair to input pixels in negative range, since through ReLU output would be 0? Would normalizing images to 0 1 range instead be a better idea? Thank you. In addition to just initialization, as the great answer of Jup 2011 notes, many analyses of artificial neural networks utilize or rely on the normalization of inputs and outputs. So normalizing the input is a good idea. Okay. Often, however, this can be done with normalization layers, layer norm, batch norm. Furthermore, you may want to enforce that the pixels are in a particular fixed range, since real images are like this. This is especially important when the output of an image is an image. When the output is an image.
I'm back.
Hi. I'm in the middle of something here.
Okay, I'm just going to continue petting this dog.
All right. Using Sigmoid produces values in 0 1 while using tanhe does so in -1 1. However, it is often thought that tanhe is better than Sigmoid, for example, here and here and here. For cases when the output must match the input, using -1 1 may be better choice. Furthermore, though not standardized, the range -1 1 is still 0-centered, unlike 0 1, which is easier for the network to learn to standardize, though I suspect this matters only rather early in training. The answer is no, mainly because the nonlinear activation happens after other layers first in nearly all cases. Usually those layers, fully connected, convolutional have a bias term which can and will shift around the range anyway, after some additional, usually linear transformation occurs. It's true, however, as the other answer previously said, in practice it doesn't have much difference which of the two you choose. However, theoretically it is better to scale your output -1 1 than 0 1, and I'd argue that it's even better to standardize your input sigma 0, sigma 1.
So, so tell me what you found out.
Many things.
All right, normalizing 0 to 1 versus 1 minus 1. What's the difference?
Usually there shouldn't be much difference in how you're normalizing, but these things matter in ML techniques. Normalizing the pixel range from 0 to 255 to 0 to 1 makes the convergence rate faster. Here you can do ranging between -1 and 1 well. I have used this range in a lot of problems and they are not as such. So is it just so that it expands the range? You know, like you can get more values into -1 to 1 because you get double the amount of space essentially?
I see.
Maybe that's the point. I'm not sure. Right? Because you have to fit all the data points in there somewhere.
So it says
I don't understand.
Yeah. Normalizing the picture makes convergence rate faster.
ReLU is max 0x, which works better when you provide negative values as well. That's the whole point of ReLU. The problem with Sigmoid is of vanishing gradient. It's not 0-centered, which gives something zigzagged gradient. Updates for the weight you can look at.
The only choice you're left with is to use Sigmoid function, which does not perform that well compared to ReLU and Talon functions. The problem with Sigmoid is a vanishing gradient, and it is not 0-centered. Someone gives a gradient.
Not sure. Converge more quickly compared to a 0-1 normalization, because bias in the model will be smaller and thus need less time to reach if they're initialized at 0. Because some values are below, so it doesn't go as high. like not so many values are going to be above 0, because if you normalize across below 0 and 1, half of the values are going to be below 0.
If you normalize between 0 and 1, half the values are below 0. I don't.
No, if you normalize between -1 and 1. If you normalize between 0 and 1, all of the values are above 0 by definition, right?
And we're trying to get them to 0. No.
I don't know, but it seems like maybe the initialization starts around 0 and then plays around, and that's what it means with that it converges slower if it needs to like go a lot of steps up to 1. But if it's like something below 0, maybe it jumps around and doesn't have to go as high by covering as many values.
What's the point of this? So I guess like let's take a step back and like what is, because these are the activation functions.
Yeah.
So what is the activation function? What's the purpose of it?
Yes, we should know that by now.
So isn't it like the purpose of that sigmoid curve is to get that exponential? So the higher, the lower values, the ones that don't activate as much will be much closer to 0. And the ones that, so the activation function, from my understanding, is when it like senses something is part of the image, right? When it senses that this turkey is here, right? It'll be high in the activation function. That's why we're using an exponential. If we're going from, and we were using between 0 and 1 because 0 is just like exponentially nothing, and then somewhere in the middle is like, we don't, you want it to be kind of separate between 1 and 0 is my understanding. Now adding this additional like point below it, maybe it's to like further separate the poor activating results because it's -1,
which means like it's less
maybe it's
likely to activate it even.
It's giving more space for, like, maybe we care more about the middle values because we're giving twice as much space for them to kind of figure themselves out between the exponentially -1 to the exponentially 1. I don't know.
Yeah. Just looking at how they define it here. The activation function of a node defines the output of that node given an input or set of inputs. A standard integrated circuit can be seen as digital network activation functions on or off depending on the input. This is similar to the behavior of the linear perceptron in neural networks. However, only nonlinear activation functions allow such networks to compute non-trivial problems using only a smaller number of nodes. Such activation functions are called non-linearities.
Yeah, from that explanation, it sounds like we're just giving it a little bit more breathing room with that extra 1. Which tells me that we care about that curve, or we care about the straight line, right? That slope between the drastic curves more. I don't know why, but this is just what I'm kind of picking up on.
Okay. Cool. Sounds good. Sounds like yet another detour.
Yeah, just put somewhere in the notes to say, Martin explain why the range -1 to 1 to Nick. Make sure that Nick understands it somewhere.
Wait, sorry, I missed that, but it's okay. We can just move on. Okay. I'm not gonna.
No. Let's move on. No, it's fine. I will just do my own research on it, and I will make sure that I understand it.
Should I make a note for you?
I don't open these. I don't go back here.
Okay, I see. Oh yeah, well.
part of me wants to say I wish this was easier for me to open, but it's not like it's difficult. We both have access. It's the shared account access.
Yeah. You just go to Google Drive and open it. That's all.
Yeah. I just need to like maybe in Asana put like tasks on.
You could even open it from GitHub if you wanted to, because I've been pushing it there.
There's too many options at this point.
Whatever you want.
Now it's too much. Yeah.
Man, it's like...
I'm just gonna let you do it.
Right. We didn't specify a loss function, which means we're getting whatever fast AI chooses as the default. Let's see what they picked for us. Flattened loss of messy loss.
The mean squared error loss.
Yeah. This makes sense, since when coordinates are used as the dependent variables, most of the time we're likely to be trying to predict something as close as possible. That's basically what mean squared error loss does. If you want to use a different loss function, you can pass it to CNN learner using the loss function parameter. Note also that we didn't specify any metrics. That's because the MSE is already a useful metric for this task, although it's probably more interpretable after we take the square root, of course. We can pick a good learning rate with the learning rate finder. Oh, we did that last time. Find it. Find it for us. So I'm probably not wasting that much carbon by doing this training here on this tiny data set.
I think you need to just put $1 in the jar.
Is that $1?
I don't know.
Whom do I give it to?
Put it in a jar.
In a jar.
Or go plant a
And then
tree. Go plant some flowers outside. Go plant a tree.
I do that. Yeah. No. I planted a lot of trees when I was a kid.
Did you?
Maybe I still have a bit of...
On like property, like your parents' property?
Yeah. It's a wood now. It used to be a garden.
And now it's a forest.
Yeah.
It's all because of you.
I always got very sad when there was like some tree, like, you know, a sapling that would grow somewhere where it was about to get, I don't know, maybe the field was about to be plowed again. And there was this little tree sapling. I was like, you just started living. So I moved them. That's why we have a lot of trees. Okay, so this looks like, well, the loss goes up a lot. What would you say, somewhere in here?
For what? What are we?
For the learning rate.
You're asking what I think the learning rate should be?
2e minus 2.
Yeah,
Oh no, 1e minus 2. It's saying 2e minus 2, but then we're trying 1e minus 2. You think, which one do you think is better?
Scroll up a little bit. Let's see where 1e and 2e minus 2.
Yeah, what are they?
That's kind of like 1 minus.
What's this
2?
minus 2? What is that?
I'm trying to think. Minus 2 means it's 10 minus 3. So yeah, it's like right where 10 minus 3. 1e minus 2 is 10 minus 3.
Okay,
So
gotcha.
2e minus 2 is just 1 over, like one tiny bit. One of those lines right over. Somewhere there.
Yeah?
Yeah.
Huh. Why would you pick this? And not somewhere here?
Why would you pick somewhere there? Don't you want the lowest point?
Oh. Yeah, why not pick that? You're right. We want the loss to be low.
Right. So for this,
maybe
tells
that's too
me
dangerous.
like, yeah, maybe the learning rate is, well, because you want a learning rate that's, I guess, maybe small. It's better to have a smaller learning rate than a bigger learning rate, right?
Yeah, the bigger ones have the danger of jumping over, right?
Yeah. And potentially never.
Never converging.
Yeah.
Oh, we're already training. I forgot that that's what we're doing here. I see. Generally, when we run this, we get a loss of around 0.0001, which corresponds to an average coordinate prediction error of 0.01. This sounds very accurate, but it is important to take a look at our results with learn.show results. The left side are the actual ground truth coordinates, and the right side are our model's predictions. Pew, pew. Pew, pew.
It's close.
That's not our model, though. Don't look at it.
No, I know. Well,
Don't look at it.
we can compare it. Well, we could have compared it to our model.
No, we should not. We shall not. Okay. It is quite amazing that with just a few minutes of computation, we've created such an accurate key points model and without any special domain-specific application. This is the power of building on flexible APIs and using transfer learning. It's particularly striking that we've been able to use transfer learning so effectively even between totally different tasks. Our pre-trained model was trained to do image classification, and we fine-tuned for image regression.
That's pretty cool.
Interesting. Yeah. It is.
I still don't understand what image regression completely is, but I think I'm sort of starting to get it.
Isn't it just that we output numbers?
Right, like in this case, it's the coordinates that we're
Yeah.
outputting, right?
Was that what it said at the beginning also for regression?
I don't know. We thought it was, well, I thought it was anyway, like the number of apples in a bowl of fruit.
Right. Several numbers, a quantity instead of a category.
Mm-hmm.
Second is when your labels are one or several numbers. A quantity instead of a category. Yeah, I guess. It sounds still like it could be number of apples. Like that would still be called regression, maybe.
Maybe.
Maybe not.
Who knows? Not us.
Not us. Oh dear. Chip, 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 chip.
Okay, so this may take...
So it's going to do 2 more rounds here.
Yeah, so another
10
minutes or
Okay,
6 minutes.
give us the conclusion, Nick.
Conclusion. In problems that are at first glance completely different, single label classification, multi-label classification, and regression, we end up using the same model with just different numbers of outputs. The loss function is the one thing that changes, which is why it's important to double check that you are using the right loss function for your problem. FastAI will automatically try to pick the right one from the data you built. But if you are using pure PyTorch to build your data loaders, make sure you think hard what you have to decide on your choices of loss function. And remember that you most probably want NN cross entropy loss for single label classification, binary cross entropy with logistics logits loss for multi-label classification, and mean squared error loss for regression. That's a nice little note. That's like a nice conclusion.
Mm-hmm.
Cool.
Very nice. How could multi-label classification improve the usability of the bear classifier? It could tell us whether there's a little child in the picture as well that we have to go and save.
It could tell us if there's a child and a teddy bear that we could say this is a nice photo.
Oh yeah, and maybe it's a happy child.
Right, maybe it's a danger notifier. So if it's a bear danger, child bear danger notifier. And
It could be
if it's anything other than a teddy bear, danger. Teddy bear, child is safe.
But also
We just
child
have a
alone,
bunch of
safe.
we just have a bunch of photos of like kids holding teddy bears, and then like a kid's hugging a bear, and like a grizzly bear. But like they're both
Yeah, that
like
would be
super
unsafe.
happy, and it's like unsafe. I don't know. You've seen like those photos or videos in like Russia that they have the like the bears are like waving and they're playing with a ball and they're riding little bicycles and they're being super cute.
I've seen it on like movies, past movies that were made to look like they were from the past.
Mm.
I think not in real life. While living in Russia.
All right. How do we encode the dependent variable in a multi-label classification problem? Martin?
In a list,
I got the easy
a list
question.
of strings, right? A list of strings.
A list.
I think
of
that's what it was.
Strings. How do we encode? Oh, this was last week's lesson.
Right, but I think that's what we did, right?
Yes. And
I mean,
in
if I
this case,
understand
it
the
was a
question
list,
correctly.
yes, it was a list of strings that they were space delimited as a value in the CSV, and we took that out and we separated it as a list of strings. Right. Okay.
How do you access the rows and columns of a data frame as if it was a matrix?
That was the similar like notation for the colon with a comma number, right?
Yeah.
So like colon, you have the range, and then you wanted a specific column.
What's that? That's it. ND array structure or homogeneous iterable or data frame. Dictionary can contain series, arrays, constants, or dictionary-like object. Okay, let's do it with a dictionary. A one, two, B, 3, 4. Does that work? Oh, you're still training, huh? No, you're not.
Finished.
Okay.
Just finished, yeah.
So yeah. So data frame, and then we could access it. What did you say? How did you say to do it?
Was it like TDF? And then the first was it parentheses with a
Square
colon,
brackets.
square brackets, colon, comma, 1, let's say. And that should give us the B column, right? No.
So you wanna, so this says all the rows, I believe.
That's
And then this says the columns, and I think you have to give a slice always. So you would say from the first one to the end. That should work. No, it doesn't. One and none is an invalid key. TDF. So this should show us everything, unless we're completely wrong.
Yeah.
Okay. That's confusing.
If you just put TDF
Is it just 1?
0. Oh yeah, what does that show?
So
That's
this gives us
everything.
the whole one. Okay. And now if we do 0, we should just get maybe the first row. No, that doesn't
It's gonna
work.
be an error, right?
So and if we say 0 to 1,
That should give us the whole thing.
so that gives us
Oh,
the first row.
excluding, yeah.
0 up to and excluding. Yeah, so this slices the rows, the first thing, but I thought the second thing slices the columns.
Yeah, like if you did comma 0 there, we should just get the first one. That's what I thought.
So we thought.
Yes.
Okay,
Anyway.
that does not work. Test. Wait, I think we had a test data frame somewhere up here where we were trying this stuff out.
Right there.
I look
right
here.
there.
So why didn't that work? So
iLock.
iLock. We gotta do iLock. Okay. Gotcha. Okay. So otherwise this doesn't work, it seems.
Mm-hmm.
Okay, good to know. So maybe the same thing works if we do iLock. tddf.iLock. And then we should just get 1. Yeah. Okay.
Cool.
iLock.
All right, let's check out this model.
All right. Here we are. Training loss pretty low.
Mm-hmm.
Around 0.0001, which corresponds to an average coordinate prediction error of. So our actual.
That didn't really do anything. So our validation loss
is actually lower.
Is lower. Yeah.
I mean, whatever, right? This sounds very accurate, but it's important to take a look at our results with learner.show results. The left sides are the actual ground truth coordinates, and the right side are our model's predictions. Dataset DS index 1, number rows 3, figure size. Okay, show results. 1, 2, 3, 4, 5, 6.
It's very close. It seems like it's.
Yeah, it's pretty good.
The last one is the one that I can only tell the difference on. That's so much.
I haven't learned, huh?
Yeah.
Max. Well, this doesn't even give 9. 1, 2, 3, 4, 5, 6, 7, 8.
Yeah, because you got
And
n rows, 4.
Yeah, but that shouldn't matter, right?
Yeah, it's the number of rows because target on one side, prediction on the other.
Right. Who's... Yeah, so there's only 1, 2, 3, 4, 5, 6.
No, if you put 6 rows there, you're gonna get 12.
No, I don't think so. We're again running into this same thing. Oh, you're right.
Yeah. And then change the figure size so that it can be bigger. No, columns you're going to get 2 because the column is the target and the prediction. Yeah.
You are right. Okay.
So
Martin is just starting to understand.
So change the figure size to be
whatever it was before.
Much wider. Yeah. Okay, so change the figure size to be like 15 by 8 really quick. I think the first one is the width, right?
I think so, yeah.
Yeah, okay. And then that.
So that doesn't really matter, so we could do that.
So put it like 15 because you want it wide, right? You want the images to be big. So do 15
right, yeah.
And then do like 50 or something. Something just obnoxious. Well, so we could like scroll down and see the images a bit bigger. There you go.
Okay. Let's look at you. Target prediction. He looks so sad. This one is a little down.
Yeah.
This is very accurate. You would say? This looks very accurate. Yeah, you're right. It's a little more
like
on the left. This looks also very accurate. Oops. And then we are stuck. Oh, no, there you go. This one is... Yeah, they're all pretty good.
They're pretty good, yeah.
I would say. Okay. Do you want to look over this some more, or you're all done?
I'm pretty good. I'm getting like
Cool.
kind of
Call it a
fried
day?
a little bit. Yeah. Yeah, I'm good calling this one a day. This was cool though, because like it was interesting also just working on a different problem on a different data set with getting like the coordinates correct.
Yeah, that's interesting. Agreed.
It was like a fun kind of problem. Yeah.
Yeah, it's nice to maybe start moving away from just doing classifications all the time.
Even though
I think
Thursday,
we're gonna do some more classification. Is that the plan?
or we could just think of something else too. But we should be prepared with the data sets and API keys.
All right. Yeah. Agreed.
Yeah. But no, this was
so something multi-label classification, or maybe some regression, maybe, if we understand it enough that we want to give it a try.
I have a feeling it's going to be some sort of multi-label classification, because I think those data sets will also be easier to find with like training and validation sets for those the multiple labels. That, and also I don't think we're going to fully understand image regression by Thursday. I have a feeling I'm speaking for myself because I also have to put a lesson together for Martin as one of my points to explain it to him. And as we learn, I don't open this file after this stream or just ever. I'm never the one who opens this. But no, I think we should do a multi-label classification. I think that'd be cool. We could do, if we do the dog breeds to classify the two dogs, I think that is like the last nail in the coffin. We close it up and we never touch dog breeds again.
But how would we actually do that? If you think about it, like we'd have to get, because would that work?
I think my naive approach to this, to get, and it's not real multi-label classification, but I think if we did nothing different to the dog breed classifier now, and we took a photo of the two of them, and we fed that photo in, and somehow we tweak the settings to show what do you think, like the what do you think it is, and then what's the first runner-up, and I think both of them will be those two breeds, and it'll be whichever one is like more predominant in that photo.
I'm not sure it works like that.
You don't think it would recognize Regs as a Chesapeake Bay Retriever if there were other dogs in the photo of him that were maybe like
because it
back,
mixes, it just thinks of the pixels
pronounced
on there.
I know, that's what I'm saying. Like if he took up most of the pixels,
maybe.
That's what I'm thinking. That's what I'm saying. It's naive. That's not the correct way of doing it. I think if we were to do it, we would have to find this multi-labeled.
Yeah, I was just wondering, can we like change this data set in a way so that it would qualify as a, because what we need is like, we could do some, we have all the data of like, of like singular dog breeds in a picture. We could theoretically just stick these images together,
Sure.
And then say, look, this is a training image for where you have this dog breed and that dog breed in there.
So put the images together, resize it.
Yeah.
I
don't know. That's just something that comes to mind for me. We could like combine.
That's like a step further of like we're getting into more intelligent solution, but I think it's still the naive approach. It's like the hacky, like let's do it really quick type approach. I think and that's just me saying that because I don't know if the photo being in a more natural state helps the classifier in any way.
Not like with a stark line in the middle.
Correct.
Where there's one completely different picture than the other one.
Yeah.
I wonder. Yeah, I don't know.
Something to think about. But
Live on the next stream.
hopefully a little bit before now and then.
All right.
But yeah, all right. We'll see everybody on Thursday.
Bye bye.
It'll be a surprise. Maybe we'll do turkeys again.
It's probably going to be turkeys.
All right. Bye, everybody.
Bye.